Yes, we use the chain rule a lot in derivatives. And so now we explore chain rule in two variable circumstances. Here's how that goes. The way I represented it, one way we can represent it is, yeah, say if we've got a function that involves an inside and outside part, what we saw was the derivative is, well, you do the derivative of the outside, do the inside the same, and then multiply that by the derivative of the inside. Well, that's sort of what we're going to do here, but let's look at it in a little different way, I guess, or a little different notation. Let's let u equal that g of x function there, and so we've got y equals f of u. And so when I do my derivative, I would have f prime of u times then the derivative of u, right? Well, the term notation that we're going to use is more along the Leibniz notation, and so what I'm finding here is I'm finding dy over dx. And so to write this in more Leibniz way, here's what it is. This is, so y is equal to f of u, so f prime, that's dy. But in essence, now I've got f written in terms of u, so it's dy with respect to u, the derivative of y with respect to u. And then this y prime, well, y is in terms of x, so that's just du over dx. And so this is more notation-wise what we're looking at for the chain rule. So this is another form of the chain rule that we didn't quite use, but will come in handy for the functions we're going to talk about. All right, so the deal is now, so that's basically, we've got y in terms of one variable. Both functions are in terms of one variable. Well, what happens, so what if z equals a function of x and y, say, and then x and y are themselves functions of another variable. So what if that is the case? We've got z is a function of two variables, and then x and y themselves are functions of a different variable, call it t. Well, more or less, what we've got here is we could very well write it out, but z, since z is a function of x and x and y are functions of t, I can think about the derivative of z with respect to t, can't I? Can think of that scenario right there. Function of z with respect to t. Well, we could go through it and calculate this or figure this out with the definition of derivative, but here's what it turns out to be. Derivative of z with respect to t, I've kind of got to go through the the same thing I went through here, because, like I said, z is a function of x and y, and then x itself is a function of t, and so here's what it is. So if I think about a derivative here, you know, this, we talked about that when we have a two variable function. You don't really talk about just a derivative with respect to x or a derivative with respect to, you think of it in partials, right? So I've got two partial derivatives off of this one. I've got a partial with respect to x, and I've got a partial with respect to y, right? And so basically what I have to do is do those separately. But since, let's just consider this one. Since this, I'm doing the partial z with respect to x, now I need to go to the x here. X is in terms of a t, so I've got to do the derivative of that, of x with respect to t. That's the first part of it, and then same thing goes, I could do a partial of z with respect to y, but now basically by chain rule to get to the derivative with respect to t, I've got to go through this one, so now I've got to do, so like I said, it can be proven by the definition, but I'm going to go through that. One other way we can visualize this, it's a tree diagram. So we've got z here, and z is a function of x and y, but then y and x are functions of t, and so what each one of these represents, so you've got your derivative of x with respect to t, and then you got your partial of z with respect to x. And so you just kind of got to follow the tree. If I'm wanting the derivative with respect to of z with respect to t, I've got to follow the line. Which may not be totally necessary, but in this particular case. But when you get more variables and things involved, it can be helpful. So that's our tree diagram. So let's just do one here. See how it all pans out here. All right, so let's find dz dt. dz over dt if z equals x squared y and x equals cosine t, y equals sine t. Yeah, so it's, like I said, it's a two-step process. First of all, we go through the x's. So we do the partial of z with respect to x, and then do the derivative of x with respect to t, and then do the ones with the y's. Partial of z with respect to y, and then dy dt. So yeah, the derivatives are, follow the same rules as we've been talking about. Again, this is a partial because x is in terms of both, z is in terms of both x and y, so that's why we use the partial notation, and then this is, x is just in terms of t, so that's more direct derivative. But anyway, what's the partial of z with respect to x? Well, the y is fixed, so just doing the derivative off the x, that'd just be 2xy. And then the derivative of x with respect to t, negative sine t. So it's just pretty much doing what we know about derivatives. All right, then the partial of z with respect to y. And so now we reverse it around. The y is our variable, the x squared is fixed, so just be x squared, yeah. And then the dy dt, derivative of y with respect to t would be cosine t. And, you know, that's one way we could write this. If we wanted to, you know, x, you know, this is with respect to t, we could put it back in, we could put it in terms of fully t, because x is cosine t, y is sine t, so I could replace those by that t expression, but I don't think the book makes you go to that link. You can just leave it here, just realize, yeah, this really is in terms of all t, because, you know, if you plug in the x and the y to be those expressions in t, you can get it all in t, but yeah, that's what you gotta do. Just kind of go through each part. The other thing I would point out is I could very well start by plugging in cosine t here and sine t here and get the derivative that way. Usually though it works out if you do it, if you don't do that, because that just makes the function more and more complicated. So, but that would be another way of doing it. All right, let's see. All right, so let's suppose x equals e to the 2t, y equals t squared minus t plus 4. Suppose that represents the path the particle is traveling. And z equals x squared minus sine xy is the temperature at each point x comma y. All right, number one, find dz dt. So same thing, we're just going to find the derivative of z with respect to t. So again, we just have to go through the pieces. Z is given in terms of x and y, so we need to do the partial of z with respect to x times dx over dt plus then the partial of z with respect to y, dy times dy over dt. Same thing we just did. So the partial of z with respect to x would be 2x minus cosine xy times, and the derivative of the inside would be y, times then the dx over dt, which would be e to the 2t times 2. With me on that? Then I would do the partial of z with respect to y. So, so that would be here. That's the y is the variable, x is fixed, so the derivative of that would be now 0. Then we'll do that, so it'd be minus cosine xy times the derivative of the inside would be just x. Then I do the derivative of y with respect to t, so that's 2t minus 1. Probably not a whole lot you can do to clean that up. 2e to the 2t times 2x minus y cosine xy. That was as good as it get there. Over here, probably could say minus x cosine xy times 2t minus 1. That's about it. Yeah. Yeah, and that's a good example of one that this way it's fairly complicated in itself, but if I tried to put, then let's put in x to be either 2t and then the y to be t squared minus t plus 4, that'll make it even worse, I think, or even more complicated. So it's usually best to do it breaking it out like that. Now, the second thing, all right, so let's talk about what does dz over dt represent? So it's just getting back to the basics of what is it we found here. So, yeah. It's a derivative with respect to t. Really what it is. So dz over dt represents the same thing it's always represented. It's just going to be the rate of change of the temperature, because z represents the temperature, right? As this particle travels along the path. Which is given by the x and y equation here. So yeah, it's the rate of change. It's still the rate of change. It always was. Okay. All right. Any questions on that? Okay.